Hi, welcome to Modern Optimization Methods. Today we will introduce Chapter 7, the Theory of Constraint Optimization. This is the outline of Chapter 7. We will introduce the idea of local and global solutions, and by demonstrating some examples, we will study the tangent cone and constraint qualifications. Both of them will lead to the first-order optimality condition and second-order optimality conditions. Finally, we will introduce the duality of constraint problems. Now, we start with the first part of this chapter, local and global solutions. We will mainly introduce the strict local solution, the isolated local solution, as well as the global solution. Now, let's take a look at the constraint optimization problem. So from this chapter, we will consider the optimization problem with constraints. Okay, we got equality constraints and inequality constraints. Here, we denote the capital E as the set of equality constraints and capital I the set of inequality constraints. The feasible set omega is defined as the points which satisfies equality constraints and inequality constraints. Now, by denoting the feasible set omega, then the problem reduces to the minimization f about x, where x in the feasible region. Okay, so this is a formulation of constraint problems. Now, a difficulty for constraint problem actually comes from the restrictions or constraints. Okay, so without constraints, the minimization may easy to get. However, with the constraints, the minimizers may change. We demonstrate this by an example here. So let's take a look at this example. We got minimizations of a quadratic function and we got some constraints. Okay, so this constraint is actually a bit complicated because this cosine x is a function which is cyclically changed. And without constraints, we can see that the optimal solution is reached at -100 and 0. However, if we get one constraint here, then from the curve here, we can see that this dotted line is the contours of function f, okay? And this is the constraints of the curve here. So with the curve, we can see that we got many local solutions at near the valley of this curve. Okay, so this actually shows that with constraints, then things may change dramatically or make us even difficult to find the minimizers. All right, so this indicates that we have to take care of the constraints in a proper way. Now, before we go on more deep theory about constraint problem, let's first give some definitions about different types of solutions. We start with the local solutions. Okay, so recall that in unconstrained minimization problem, the local solution is defined as a point x star that within its neighborhood, x star reaches the smallest function value. Okay, so this is the local solution for unconstrained problem. And with constraints, then the definition changes a little bit. So we only need to define it as a function point that it reaches the smallest function value within a neighborhood intersects with the feasible region. Okay, so for local solution of constraint problem, it is defined as that we can find the neighborhood of x star such that for the intersection of this neighborhood with the feasible region, for each point in this intersection, the function value f at x star will not greater than all the function values within this intersection. From this point of view, then X star will be the local solution. Okay? Now, let's take a look at the strict local solution. The strict local solution actually follows the same style as unconstrained one. However, we also add it with the intersection of feasible set. Okay? So specifically, a point X star is a strict local solution of a constraint problem if X star is a feasible point and we can find a neighborhood capital N such that for all the points in the neighborhood intersects with the feasible region, the function values will strictly greater than the function values at X star. This will make X star a strict local minimizer. We also refer it to as a strong local minimizer. Okay? And after we introducing the strict local minimizer, the next type of local minimizer you may get is that the isolated local minimizer, okay, which is similar to that unconstrained case. So what is an isolated local solution? It is defined first as X star must be a feasible point, then we can find the neighborhood of X star such that for any point X star is the only local minimizer within the neighborhood intersection with the feasible point. Okay? So if this condition holds, then X star is the isolated local minimizers. So as we can see that compared to the unconstrained problem, all the definitions here, we add an intersection with the feasible point. So this is the difference. And also for the relationship of local minimizer, the isolated local minimizer and the strict local minimizer, they are similar to that of unconstrained case. For example, the isolated local solutions are absolutely strict local solutions. However, the reverse is not true. Okay? So we have demonstrated an example for unconstrained case. And for constrained case, you can construct an example on your own. Now, let's take a look at the smoothness issue. So in some optimization problems, we may get unsmooth or non-smooth constraints. Okay? For example, the smoothness of functions and the smoothness of constraints is important in deriving optimality conditions. Okay? Now we focus specifically on the non-smoothness of constraints. Okay? Let's take an example. For example, if we got a constraint like this, the L1 norm of X is smaller than or equal to 1. If we write the L1 norm in the absolute value, then it is actually non-smooth constraints. Okay? However, for such kind of non-smooth constraints, we can actually transfer them into smooth constraints by writing them into 4 inequality constraints. Okay, so by different case of absolute value of component, we can get the 4 constraints here. And geometrically, the feasible region is actually formed by 4 lines in the 2-dimensional space. Okay, so we can transfer some of the non-smooth constraints into smooth constraints by adding the different number of constraints. Okay, so this is the way that we deal with non-smooth constraints. However, there are some non-smooth constraints that we may not able to transfer it into smooth one. So in this case, we need more advanced technique to deal with them. Now, if you go to non-smooth functions, it is still possible that we transfer it into smooth one. For example, if you get the function as max function, then we can introduce a variable t to make t that greater than or equal to x and greater than or equal to x squared. By minimizing the fx, then we can get that this t must equal to the max of the two terms. Okay? So in other ways, for piecewise linear function, we can always transfer them into smooth case. Now, let's make a brief summary about this part. We have introduced the different types of local solutions, including isolated local solutions, strict local solutions, as well as global solutions. And for the non-smooth case, we can transfer somehow to the smooth one. However, this technique is only applied to some of such non-smooth case. Okay? So we stop here and see you next time.